So welcome to today's lecture, which is about representation learning. And before I start with the topic, I will repeat what we were talking about in the last lecture. So in the last lecture, I gave you all the basics you will need for the next lectures, and we were mainly talking about regression and classification. And when you have a look at this machine learning pipeline, you will see that the structure is always the same. So you have an input, and the input you feed into the machine learning model, and then you get the desired output. Depending on the loss function, you will perform regression or classification or any other tasks you want to perform. And the machine learning model is learned from input-output pairs, which is called the training data, and you can apply then the machine learning models to other input data, which is of course similar to the input data you trained the model on. And one example for this given example here is that if you perform regression, you can do yield estimation, and if you want to do classification, you can, for example, perform pixel-wise semantic segmentation. So regression has a continuous output and classification has a discrete output. So today we are talking about representation, and first of all is we need to talk about what is a good representation. And I show you here a really nice example from the deep learning book of Ian Goodfellow. And so imagine I give you this Roman numerical representation and I ask you to solve this equation. And when you realize and think about what you do in your head at the moment, is not that you immediately start to calculate. What you do is you think about what is this C, what is this X, what number was it? You think back when you were in school and when you learned these numbers. So what you do in your head is you change the representation, which is most suitable for to solve the task. And this is exactly what you also do in machine learning. You want to have a representation which is suitable for your task. So in this example, you change from this Roman numerical representation to this Arabic numerical representation. Then you can do you can solve this task by long division. You learned this in school, and now this task is easy to solve. And there are different possibilities to derive a good representation in machine learning. And today I will show you a few of them. From classical one, which was used for many years, and then we will talk about neural networks and how neural networks can change the representation to a really good one. So the most classical one, or the most naive way to derive a good representation, is to use handcrafted features. What does it mean? You have features, and you have input data, you have a task, and then you think about what would be a good feature to use. When we talk about plant sciences, for example, and you want to derive biomass, the first thought which should came to you is you could use NDVI or some, the near-infrared channel, for example. So these are handcrafted features. They are manually designed, but as you can imagine, for some tasks it's easy, but for others it's not. Then you can perform feature selection. For example, when you have hyperspectral data, you have a lot of data, a lot of input dimensions. And if you do not want to use all of them, you just choose the ones which are suitable for a task and which you need for your task. So coming back to the example with the plant sciences, you use the near-infrared channel, which is very helpful, and maybe also the red channel and any other specific band from the hyperspectral data, for example, which you need. Feature extraction is similar to feature selection, but here it's not that you choose specific features from the data. It's more like you transform the whole input data you have to a new feature representation based on the input data. Best example is principal component analysis. Here you end up with a totally new representation of your data. In most cases it's much more lower dimensional than before, and so you find a representation for your task which is very suitable and which is much more easier to handle because the dimension is lower. And a very interesting part is of deriving a representation is feature learning. And about this part I want to talk today. And yeah, I will come back later to this, but to give you a definition, what is feature learning, also called representation learning. Here you learn a new data representation which is more suitable for a given task than the original data representation. And here the important word is learning. A powerful feature representation is, for example, that you have a high discrimination power when you perform classification. You want to distinguish between your classes, and of course you want your feature representation to handle this in an easy way. Robust, here I mean when you change the input data a bit, you also want your new feature representation to change a bit. It's not that you change a little bit in your input data and then you change a lot the feature representation. Lower complexity, mostly related to that you have, if you have features with or input data with a high feature dimension, you want to have it afterwards that it has a lower dimension, that means a lower complexity. Easier to interpret. Sometimes it can be really hard when you have your input data to understand what is going on in your input data. You cannot see it, you cannot visualize it, not illustrate it, and you need a specific tool to visualize it. So it's very hard to grasp an idea about the behavior of your data. So what you want is, you want a feature representation which is easy to interpret, that you know how to handle the data. And distributed, this is more related to efficiency and how you can deal with complex data. And I will explain later to you what does it mean when you have a distributed representation. But first of all, I want to show you where everything started many years ago. So when you have an image, the easiest feature you can think about is you take the intensity. When you have a gray value image, you have one value per pixel. That means the gray value, so you have one number. When you have an RGB data, you have three numbers. That means red, green, and blue. And if you have even a sensor which gives you a higher spectral resolution, you end up with multispectral data or hyperspectral data. So you have a lot of feature dimensions, and here per pixel you have many informations about the spectral characteristic of this pixel. So one pixel usually contains a lot of information, and of course you can have different centers and combine the data, and then you have even more information for a specific position. And let's have a look at this image, and I will show you why this kind of features mostly is not enough. So when you have a look at these two regions where these yellow arrows point to, you can see a lake or a small sea, small lake, and a shadow. And if you do not use context information, so just look at the pixel information, you will see the intensities cannot be distinguished. They have exactly the same value, so you cannot tell, if you only look at the pixel, if it's a lake or is it just the shadow of a building. That's why you need more complex features, better features, more descriptive features. And first you can think of taking into account the context, the neighborhood. And if you want to include the neighborhood, the easiest thing what you can do is you do not take only the pixel, but you take also the pixels around it. And because you cannot work with image patches, what you do is you vectorize the image patch, that you end up with a long vector. That means you take, for example, the columns of this image patch and you concatenate the columns under each other, so you end up with a long vector. And the larger the neighborhood, the higher the feature dimension. So one feature dimension belongs to one specific point in the neighborhood. Of course, you can also do it with segments, but this is much more harder because the segments need to have the same size and the same shape if you want to do it in the same way for each pixel position. And another problem is that if you do this, it's not rotation invariant. That means when you have a look at these two image patches here, you can see I took an image patch and then I rotated it. And when you illustrate it with the just a few values, a few gray values, here you can see if you take the columns and you vectorize it, you will see when you rotate this image patch, you will end up with a totally different feature vector, although it's the same image content, and this is a problem. And if you just think of when you take pictures, when you take observations, you cannot always ensure that you have the same orientation. So this is a problem. An alternative would be just to take the standard deviation or the minimum and maximum value of this region. So independently of how you rotate it, it will give you the same values. But of course, you will lose a lot of information if you only use the standard deviation. This is one number. Maybe for gray values, if you have RGB, you have 3 numbers, but you lose a lot of information. Another possibility is a sorted histogram. So you take all the values, the intensity values you have in this image patch, and then you decide on the number of bins for a histogram. And then you count the number of pixels which belong to specific bins, and then you can use the histogram. And as you can see here, if the image patch is rotated, doesn't matter, you will end up with the same feature vector. But here the problem is how to choose the hyperparameters. Hyperparameters means that you need to decide on the number of bins. And of course, not to forget, you need to normalize the histogram afterwards. So if you have, for example, different sizes of the neighborhood, you cannot work with absolute numbers. You need to normalize the histogram, for example, that the vector sums up to 1 afterwards. And another interesting feature is texture. And here you can see a nice example from different agricultural fields from all over the world. For example, Minnesota, Kansas, Germany, Bolivia, Thailand, Brazil. So starting in the top left corner, and then you go through it. You can see these patterns belong to these countries. So Germany, I guess you can see which pattern belongs to Germany. It's the upper right one. And yeah, you can see, we can see, and I hope you too, that these patterns differ from each other. But if you want to transform this, they differ, into something the machine can read, you need to think about a feature. And this is, for example, structure. And a quite old approach to capture a structure in an image can be seen here. It is quite old, from 2001, but I think this is very important to know for you, because this principle will come back when we talk about convolutional neural networks. What you can see here are so-called filter banks. Filter banks are nothing else than a collection of convolutional filters. And these convolutional filters contain mostly filters, or they contain values that you end up with some edge detection, or but also a combination of Gaussian filters and edge detection filters. And so here you can see two very famous filter bank. The one is the Leung-Malik and the other one is the Schmidt filter bank. And as you can see, the Leung-Malik has a lot of edge filters and also some Laplacian of Gaussian. They are also called Mexican hat, because if you when you plot these Laplacian of Gaussian, they have a shape like a Mexican hat. And the Schmidt filter bank consists of rotation invariant filters. And so again, when you think about, it's important to capture the image content independent of the rotation of the image. This is one example. And in the Leung-Malik, this rotation invariance is somehow captured by that you have different orientation of the filters. So how do you now use the filters from the filter bank to extract a new feature representation? What you do is you take one filter and then you perform a sliding window approach, perform convolution, and for each position of the filter you get an information, and this information, if you do it for the whole image, piles up to such a filter output, which is again a feature map of the size of the image. And if you do this for each filter, you end up with a lot of these filter outputs, one for each filter, and this is your new feature representation. And now there are some other possibilities. You can derive a new representation. It still has a lot of handcrafting in it, but I will tell you a little bit more about what tools you can use instead, just thinking about what would be interesting to solve your task. And I will talk about summarization, approximation, and transformation. And of course, important information. It's not that you end up always with a new representation which is lower dimensional. Sometimes it can also help to increase the feature dimension, especially if you think about the discriminative power. Sometimes it's much easier to go in a higher dimensional space and then perform classification than staying in a lower dimensional space. So, summarizing features, let's have a look at such a hyperspectral signature of a healthy plant. You can see this first bump. This is the area of the green, or the green visible area. That's why plants are green to us, and the high near infrared value. And here it's easy to summarize features. For example, you can do this. You just have a look in, where does the signal not change a lot? Important regions in the signal are, of course, the area from red to near infrared. That means around 700 nanometers to 800 nanometers, because you have a high change in the signal. But for example, if you go from 800 to 1000 nanometers, you will see the signal will not change a lot. It will give you not more information if you use all these channels, all these bands. So you can just summarize it, for example, by just taking the mean in the specific area. So you can shrink the feature dimension by summarizing a few of these channels. So another possibility is to approximate your features. So how can you do this? I will show you on an example where you have a fluorescent signal. A fluorescent signal is similar to a hyperspectral signal when you think of the information you get about a plant. But fluorescence is the emission of light of matter that has absorbed light or some electromagnetic radiation. And you can see here a typical fluorescent signal of a plant. And what you do is you approximate this signal with a polynomial regression. And then you take the values of the parameters which define the polynomial regression model, and this is your new data representation. And of course, you do not need so many parameters for this regression model. You will end up with a much more compact representation of your data, but still it describes your data. And this is a totally other representation, so it's even more transforming your signal than if you only have a feature extraction or feature selection from your original input with, for example, PCA. And on the top, you can see this approximation, and on the bottom on the slide, you can see the reconstruction error. And you can see that in some parts, the reconstruction error is quite high, but you can do something about it. For example, you take piecewise polynomial regression. So you combine a little bit this summarizing features and this approximating with this regression model. So you think about parts of your signal which could be approximated by a very simple polynomial regression model. And then in each of these parts, you estimate your model, and then you store these coefficients. And if you concatenate all the coefficients of the models, you end up with a new data representation. And in comparison to the other model where you have one model for the whole signal, you can see the regression error is much lower. So this is a really nice idea. It works quite well for signals, but it's not always the case that you have such signals. So generally, it's a very good idea to think about the features you want to have and the machine learning method in combination. So there's some kind of rule of thumb you should keep in mind. And this is when you have complex features, it's mostly enough to have a simple method, such as a linear classifier or a linear regression model. But if you have only simple features because you cannot do anything else in this task, then you normally need a complex method to solve your task. In the next part of the lecture, I want to show you a method for feature extraction, which can also be used for many other tasks in machine learning, and it's called sparse representation. Sparse representation says nothing else than each signal can be approximated by a weighted linear combination of basis elements. So the signal here denoted with phi can be a pixel or an image patch or something else some entity you can extract from your data. And then you have this dictionary D, and each column in this dictionary D is one basis element. We will talk about it later, how you can determine such basis elements. And you have this activation vector alpha. Alpha contains the weights of the linear combination, and as you can see here, most of the elements in alpha are 0. That's why it's called sparse representation. And alpha can be determined by one of the equations given below on the slide, and both of these equations, you can see the first part is the same. So d alpha is the approximation, phi is the signal, and you want to minimize it. So you want this reconstruction error epsilon to be as small as possible. And then you have some constraint. And the constraint is that you want alpha to be sparse. You can do it, for example, with a zero norm. That means you restrict the number of non-zero elements by W. And the other possibility could be that you use an L1 norm, for example. This also enforces sparsity, not the L2 norm. So L2 norm will not give you a sparse solution, but for example, if you restrict your alpha to that all elements need to be larger than zero, in many cases it happens that some of the elements are zero. And let me give you an illustrative example. So here you have given an original image, a very simple sketch of a fish. And then you have this dictionary. This dictionary, it's a compact illustration. So each patch is actually one column in the dictionary if you want to make calculations with it. But for illustration purposes, this is a very compact and nice illustration of the dictionary. And what you can see is the original image. Then you have the reconstruction using exactly this dictionary, and illustrated is the reconstruction error. So how do you do it? You make a sliding window approach. So you take one image patch from the image, and then you approximate each of these image patches by a weighted linear combination with the elements of this dictionary. And given below, you can see one example. So this is a patch from the eye of the fish. And on the left side, this is the original image patch, and right next to it, there's the approximation. And in this algorithm, two elements from the dictionary are used with the given activation weights. If you increase the size of the dictionary, you will get a better approximation because you have more possibilities to approximate each image patch. And you can see here, in comparison to the smaller dictionary, that the reconstruction error is much lower, and also you can see more details in the image. Given below is the approximation for the same image patch again, and now 3 dictionary elements are used, and also you can see the approximation is much better. So in the context of remote sensing, you can find the principle of sparse representation when you have a look at unmixing. So when you think of hyperspectral data and multispectral data, you will see that if you compare both of them, that hyperspectral data has a higher spectral resolution, but a lower spatial resolution in comparison to multispectral data. As a consequence, if you have a look at one pixel, for hyperspectral data, you have a lot of land use and land cover information captured in the information of one pixel. If you want to know what is in this pixel, you need unmixing. What you need for this is pure spectra, so some prototypes of materials, and these are exactly your dictionary and elements. In the context of unmixing, they are called end members. And normally you also know the class of it. So you, for example, know that it belongs to a specific material. And the activations are exactly the fractions of the classes. So when you unmix it and you take the weights, you can relate them to the fractions. Of course, in this context, you need additional constraint, for example, that they sum up to 1. Otherwise, it makes no sense from a physical point of view. So you cannot mix information to more than 100%. And also all of these fractions need to be larger than 0. So when you want to use sparse representation for representation learning, you have a look at your original data representation and your activation vector. And the original data representation is your input data, and the activation vector can be used as new data representation. And here, depending on how you choose the dictionary, you can control how your new data representation is. For example, you can enforce it to have a lower dimensionality. If you want to use it for dimensionality reduction or for signal representation, you need to take care that the reconstruction is as low as possible. So the error epsilon needs to be small, and the dictionary needs to be undercomplete. Undercomplete means that the number of columns is smaller than the number of rows, so you do not have a lot of elements in this dictionary. If you think about classification, you have other goals for your representation. So you want to enhance the class discriminatory information, because you want your data to behave in a way that it's easy for you to distinguish between the classes. And so you have a look at the classification accuracy in the end. So you want a representation to reach a high classification accuracy. That's why always think about the task you want to solve when you choose the representation of your data. Now, there are two big questions when it comes to sparse representation. The first one is how to choose the activation and the weights, because this is your new data representation. And the other one is how to choose the dictionary elements. And as you can think, you cannot separate these two tasks. You can solve them independently, but one will influence the other and vice versa. So we can solve these big questions. So the first question was how to choose the activation and the voice. And here, this is called, this task is called sparse coding. So the whole process, the whole representation is called sparse representation. But when you talk about the determination of the activation vector, you talk about sparse coding. The most commonly used methods for sparse coding are matching pursuit, orthogonal matching pursuit, and non-negative least squares. And the other big question is how to choose the dictionary elements. And there are some simple methods like just choose artificial dictionary elements. But another really cool technique is dictionary learning. And for dictionary learning, you can use, for example, K-SVD. And as the name says, it uses singular value decomposition. And the other one is archetypal analysis. Of course, there are others. But archetypal analysis have a look at the archetypes, the extreme points of a data distribution, and they are used as dictionary elements. So in the next slides, we will have a look at the orthogonal matching pursuit and the K-SVD. So you will know after this lecture about one method for how to choose the activation and the weights, and one method for choosing dictionary elements. So orthogonal matching pursuit is one common approach, and it's a greedy approach. A greedy approach is not that you find a global solution from by just solving an optimization problem. It's more like you go step by step. It's a little bit like pathfinding. So you don't see your overall goal, so you don't know what the best perfect path is to your goal. But what you know is in which direction it is good to take a next step. So you go a step, and then you see what would be a next good step, but it can happen that there's an obstacle, and then you need to change your path, and so on. In the end, of course, you hope that you reach the overall goal, and so the best solution for your task, but it can happen that you will end up hopefully close by to the best solution. So this is the a greedy approach, but mostly it will give you a very good solution. It used the S0 norm, that means you restrict the number of non-zero elements, and here again I gave you the equation for minimization. So this is the optimization problem which we need to solve. You have d alpha, which is the approximation of the signal, phi is the signal, and then you have a constraint that the alpha vector, the activations are restricted to W number of non-zero elements. So now let's have a look at the procedure, so how to perform orthogonal matching pursuit. As an input, you start with a given dictionary. So let's for now assume you have it from somewhere. We will later have a look at how you can determine a really good dictionary too. Then you have given a sample. This is exactly the sample you want to reconstruct. And you have a coefficient set I, and the coefficient set tells you exactly which dictionary elements are currently used for the reconstruction. As an output, you want to have your estimated weights, and so these are the weights of the linear combination. So you will end up with an activation vector, and in the beginning the coefficient set is empty, your iteration is set to 0, and the reconstruction error is exactly your signal, because you do not have anything reconstructed yet. To determine the first element for the coefficient set, you compute the scalar product of your dictionary and the reconstruction error, and if you take the argument of the maximum, it will give you the first best suited element to put in your coefficient set. What it does is nothing else. It chooses the dictionary element which captures most of the signal. So this algorithm always tries to reconstruct as good and as fast as possible. So this in the beginning, when you compute the scalar product, this is exactly the correlation coefficient. So you end up with the best suited element for the coefficient set, and you put it in the coefficient set, and then you compute your activation vector. You update the reconstruction error by having the signal, and then you subtract the current reconstruction. So you end up with a new reconstruction error. You increase the iteration, and you continue the procedure until you reach the number of dictionary elements you want to use, or you can even stop before if you reach a very low reconstruction error. So now you know a procedure and how to determine your activation vector. Now let's have a look at how you can determine a good dictionary for reconstruction. There are different choices for a dictionary. For example, you can use synthetic basis function, for example wavelets, or you can learn it from your data. That learning means, for example, you can select it, for example, by clustering. So you have the data points, you make a clustering, and then you just take the means from, for example, k-means. You can extract it from data with a procedure like K-SVD. I will show you in the next slides how you can do this. Or you can use some other kind of data from the same data distribution, or from arbitrary unlabeled data. So you can, in the end, you can fill your dictionary with whatever you think is important and relevant and helps you for reconstruction. And I will also show you self-taught learning later, because this is a really nice example how you can integrate further information from unlabeled data. Let's start with one of the most commonly used synthetic dictionaries, which is the Haar wavelet dictionary. A Haar wavelet dictionary, as the name says, contains Haar wavelets, and Haar wavelets a sequence of rescaled square-shaped functions, and if you apply this function to image processing, you end up with such typical image patches, and these image patches are vectorized and collected in the dictionary. This dictionary is called after Alfred Haar. That's why it's called Haar dictionary. It is of course fast to build because you have a simple function and you just apply it, and you have as many elements you want to have in your dictionary. The disadvantage is it's not very interpretable or explainable. So if you, for example, want to use it for applications similar to unmixing, it will not really help you for this task because you don't know what the elements are. They are just synthetic elements. And they have, or they generally end up with a low approximation or reconstruction ability because the elements do not really capture the structures and the characteristic you have in natural images. So therefore it's a much better idea to have data-driven dictionaries because they are some more powerful and you have a better reconstruction ability. And here you can, for example, choose k-means, which you apply to some data samples, and you just take the means as dictionary elements, or you can use K-SVD. And we will have a look at K-SVD now. And in order to do this, we have a short digression to singular value decomposition. So let us consider you have n vectors of d dimensions and they're collected in a data matrix. And you can see here the data matrix phi, and the data matrix has a dimension of n times d. So you have lying vectors and one row is one sample. And yeah, the size of this matrix is d because you have d-dimensional vectors. Now you need to subtract the mean to center your data, and you can do this by the following equation given below, and you end up with mean reduced features in the matrix phi c. And for singular value decomposition, you decompose your matrix in three other matrices. So you decompose phi c, the center data, in a matrix U, S, and V transpose. And you can see here the dimensions of the matrices and also the content. So white indicates that there's a 0, and otherwise you have some values. U contains the left singular vectors, and V transpose contains the right singular vectors, and both of these matrices are rotation matrices, and S contains the singular values. It is sorted in this way that you have the element 1, 1 is the largest singular value, and the singular vectors indicate the direction of the spread, and the singular values indicate the length of the spread. So if you have a lot of data and you do a singular value decomposition of your data, you can immediately interpret what the singular vectors and the singular values what they show you. And the singular value decomposition we need now for K-SVD in order to create a dictionary. And K-SVD is not only that you apply it and then you have a dictionary, it's more an iterative process, and you switch between sparse coding and the dictionary update. So you make an update on your dictionary that it's more suitable for reconstruction. Then you determine new weights for the sparse coding, and then based on the codes you have a new make an update on your dictionary, and so on. And it's not that you update the dictionary all at once. You have a look at each dictionary element independently. So again, we will work with the equation given below. You saw the equation before. You have an approximation dA, which is the current approximation. Phi is are your signals, and we work again with the zero norm, so we restrict the number of elements to W in the activation vector. So now let's have a look how K-SVD works. So first of all, what you do is you rewrite the reconstruction error. So the reconstruction error is given by phi minus the current approximation d alpha. And what you do is you rewrite the matrix multiplication from d alpha into a sum. And the sum goes over t elements, so you have t elements in your dictionary. Because we only look at one element per time, you look at the kth element and you want to update it. So what you do is you separate the sum and you separate the kth element from it. So what you do is the sum without the kth element is summarized in an error matrix E, and this is exactly the error resulting from all elements except the kth one. And so indicated here in this illustration below is the red column is the kth element, which we are currently looking at, and then you have the row in the activation matrix, which is assigned to exactly this dictionary element. So the next step will be that you do a singular value decomposition. What you would do is you do a singular value decomposition of the error matrix, because you exactly want to know the direction and the length of the spread of your data, because the data at the moment is exactly the reconstruction error. So you want to reconstruct the part of your data which was not reconstructed enough yet. But there's one problem. If you do it like illustrated here, you will end up with a dense update. But we want to have, we do sparse representation, so we want a sparse activation vector. And if you update the dictionary and the activation vector in a way that it gets a dense update, you will lose the sparsity. What you do is you shrink the matrices to keep the sparsity. And how can you do this? First of all, we still have a look at one element. So we're looking at the kth element indicated in red. Then you find all samples where the activations are non-zero and collect them in a matrix phi prime. So phi prime now contains all the samples which use this dictionary element. Then in the same way you shrink the activation matrix, and here it contains only the columns where you have non-zero elements. In the same way also this applies to the error matrix. So we shrink the error matrix to E prime, and because we are doing all this, we only have a look at these elements which are involved in the current reconstruction. And because we do not have a look at any other elements, if we do an update, we do not perform an update on the sparse elements in the current reconstruction. So in the end, we define this alpha k is a dense activation vector. So everything which is involved is a dense subsystem of the current equations we have a look at. So now you apply the singular value decomposition to exactly this reduced matrix. So you end up after the decomposition with these matrices U, S, and V transpose, containing this, the singular vectors and the singular values, and you pick exactly the elements which are assigned to the largest singular value, and you use this to update your dictionary element. the kth one at the moment and also the activation vector, and then you perform this for each dictionary element. And after this step, you end up with a new dictionary. And what you can do afterwards with this given dictionary, you can perform sparse coding again, and then you can do the dictionary update step again. Or you can just leave it as it is and take the dictionary for further processing and reconstructing your data. And to show you an example, you can see here a comparison of an artificial and a learned dictionary. And the dictionary were learned on images of facades. So first of all, we took facade images, then we only take the gray values and normalize the data, and then we applied K-SVD, and you can see that the dictionary you learned with K-SVD much more shows the structure of the facades, not like the Haar wavelets, which would be the same independent of the data. Okay, so now the question is, how can you use this for classification? So it's not only that you can use sparse representation for reconstruction, you can also use it for classification. And when you remember, in the last lecture, I was telling you different paradigms for classification. One of them was self-taught learning. And I told you I would tell you in the next lecture how you can use labeled and unlabeled data at the same time with a procedure called self-taught learning for classification. And I will show you now how you can do this. So when you perform self-taught learning, you use the same procedure for sparse representation I told you before. So in this case, you have given some signals, which are pixels or image patches or whatever kind of data you want to use. You have a dictionary with basis elements, and alpha contains the weights for the weighted linear combination. What you do now is you do not learn a dictionary, you fill your dictionary with unlabeled data. And normally you have a lot of them. So you can choose by clustering or just by selecting a whole variety of the unlabeled data you have. And the good thing is you don't need to know any labels, so you can just fill it and use this additional information from the unlabeled data to solve your classification task in a better way. What you want is that your new representation is highly discriminative. So the goal is to change the representation. So you go from using your original data representation to use now the activations as a new data representation. And of course, what you want to have is that it's highly discriminative. That means activations are for one class are distinct. You can see it here illustrated are different red values, and so one red value belongs to one class, and you want different activations for specific classes. And yeah, of course you want it to be more discriminative than the original data representation. Then for testing, you keep the dictionary as it is, so you fix it, you have new input data, you apply it, you make the reconstruction, you do the sparse coding as you did it for the training data, and then you use the obtained activations and feed this as input to your classification model, which you learned from the training data. So actually you have two steps. So first of all, you apply the sparse representation. So you do the sparse coding and then you use a classifier. Now let's have a look at how you can self-taught learning use for land cover classification. And as an example, you want to perform the land cover classification with a Landsat 5DM image. and it shows an area of Novo Progresso. This is in Brazil, and this area is characterized by fire clearing. That means you have a lot of deforestation, and you can see this on these this specific structures in the left corner of the image. We want to classify each pixel into one of the three classes: forest, deforestation, and arable land. And we have a look at the small area, and the small area in the indicated in green is about 900 square kilometers. So this is the sub area, and here is the labeled data, and we want to learn from this labeled data, and we want to apply it afterwards to the whole image. So for self-taught learning now, you need unlabeled data, and because Landsat data is available all over the world, what you can do is you randomly collect a lot of image patches from the Landsat sensor, and we collected, in our case, 1 million of them. And because you cannot use 1 million image patches for a dictionary, we selected a subset of it. We selected the subset with archetypal analysis. Archetypal analysis is very similar to k-means, but instead of finding clusters and taking the means, you just have a look at the data representation and you take the extreme points from the distribution. So you can think of having the data in a high-dimensional space, and then you collect all the data sitting on the convex hull of this data distribution. And to show the differences and to show you that it's helpful to change the data representation, this approach is compared to classification with a regional data representation. Also, we compared two classifiers. What you can see here is support vector machines and logistic regression. Support vector machines are a complex classifier which learns complex decision boundaries, and logistic regression is a linear classifier, so you only can distinguish between classes with a linear hyperplane in the feature space. Self-taught learning can also be combined with K-SVD. That means you start with an initialization of the dictionary with unlabeled data points, and then you update the dictionary with K-SVD. But also you can use the archetypes as I described before. And what you can see, the best result was obtained by using the self-taught learning approach with the archetypal dictionaries. And that means just smartly chosen unlabeled data points for the dictionary and logistic regression. So these results show you that when you have a good data representation, it's enough to have a simple classifier. And actually the algorithm is or the simple algorithm, logistic regression, is able to distinguish even in a better way than the complex classifier. And as a last remark regarding sparse representation, I want to show what is the connection to back of words, because the approach is similar. So when you ever think about back of words, you will see that the concept of sparse representation is similar. Back of words started to be used in document analysis, and it means nothing else than you have a representation of a text that describes the occurrence of word within a document. So you have a bag with words, and in each bag you have specific words. So you have a specific bag for specific documents. So when we have a look at the back of words approach, we deal with labeled data. And the labeled information is collected also in a dictionary, and in this example here we want to distinguish between two classes, and we want to classify if this image is a fish or not. So we have two classes. One class contains fish, and the other one contains something else, in this case vegetables. So each of the classes has specific characteristic, and what you do is you make a patch-based extraction and then a clustering. So for each class you extract packages with the sliding window approach. You cluster it, for example, with k-means, and then you use the means and as dictionary elements. And because you do it class-wise, you have exactly label information to each dictionary element. If you perform it now in a similar way with a test image, and you want to know which class it is, you do the same. You extract patches, and then you reconstruct it with a given dictionary, and then based on the activation, you can, for example, count them, or you can have a look at the value of the activation. You will see that this image is better reconstructed, or the activation point towards the class fish. So let's come back to the feature learning, representation learning, and the characteristic we were looking at in the beginning of the lecture. And I want to repeat, what does it mean to learn a new data representation? You want to learn it in a specific way that the new data representation is more suitable for a given task than the old original data representation. And some characteristic we want to have, we talked about discrimination power. You want to have it robust. Then when you change the input data, you also want only changing, you want the new data representation also only to change a bit. You want to have a lower complexity, and so on. And so let's have a look at the machine learning pipeline again. You have an input data. The input data is fed into a machine learning model, and then you get a desired output. You can use it for classification, regression, in whatever way you design your machine learning model. If you have a more detailed look at it, the classical approach is, first of all, you have your data, then you extract some features you think which are suitable for the task. As I told you, you can do this with handcrafted features, or you select features, or you can even use more sophisticated approaches like sparse representation, self-taught learning, something like this. And then you use the data representation and learn a machine learning model for regression or classification or something else. So now, when you have a look how neural networks work, they do it in one step. So you do not need to think about anymore which features are relevant for solving your task. The neural network approach learns the features and the model parameters at the same time. You only need to decide on which task you want to solve, and then the neural network and the whole optimization process determines the representation automatically. And this representation is well suited for the task because it's jointly learned. And this is called end-to-end learning. So learning from input to output in one step. You do not have anymore this feature selection, extraction step, and then the training step of your machine learning model. Now you solve it in an end-to-end manner. And neural networks are successful nowadays because, first of all, we have enough data to train them. I'm sure you heard about the big data opportunity. Then you have better computing facilities for neural networks. You need mostly graphic cards if you want to process all the data and to learn your parameters of your models. And also you have improvements from your methods. So nowadays we have a lot better, larger pool of tools how to optimize neural networks, how you can train them in a stable way, and so on. That was not possible in, let's say, 10 or 20 years ago, and that's why even they existed for a long time. They become very popular within the last days, because now all these things happened. So here you can see how the pipeline for supervised classification will look like when you use a neural network. You have given, for example, a process satellite image, and you have given labeled data, in this case for 2 classes, and now you just use the data as it is, and you feed it into a neural network, and in the neural network a suitable data representation is learned, but also at the same time the parameters for the model, in this case for the classification. And then you have you end up with a land use and land cover map when you apply the learned model to all the data you want to know the class of. And as before, in order to assess the quality of your model, you do some evaluation, and of course you're free to do also some post-processing. So neural networks are especially very good in giving you a discriminative representation, because you're tuning the data representation at the same time you're learning a model for classification. So this is a typical scenario in remote sensing. So for example, you have a green and infrared channel, and you want to distinguish between these 2 classes. You learn such a complex decision boundary, but if you learn a good representation of your data, you might be able to find such a discriminative representation. And neural networks are really good in doing this, because the feature representation is exactly tuned to work in combination with classification. And the last thing I want to talk about today is distributed representation, because neural networks are also very good in finding a distributed representation. A good representation for models captures the underlying explanatory factors of variation. That means the underlying factors which explain the data are disentangled. That means that good features are useful to explain all the variation. Imagine you took observations from plants, and while you were taking measurements, it was raining, then you have some cloudy weather, and maybe then the sun was shining. You can imagine that the spectral appearance would change, and also the features you extract from the images or whatever data you took also change. But you do not want to model all these different factors. So actually what you want to have is you want to model the features of the plant, showing you, for example, the health status or the stress level of the plant, and then you want all the influential factors from the weather. So you want to disentangle the relevant features of the plant and the other, all the rest of the other features. And this is exactly what is done with the distributed representation. So the opposite of a distributed representation is a localist representation. And here's an illustration from a nice book showing what a localist representation is. Imagine you have some geometric shapes. In this case, you have rectangles and ellipses, and they have different orientations. So they are vertical or horizontal, and if you want to represent all of them, you need a specific representation for all of these combinations. So you need a representation for the vertical rectangle, for the horizontal rectangle, and also for the vertical ellipse and the horizontal ellipse. Every time you change this shape a little bit, you need a new dimension, a new data representation for it. Now what you can do is you can use a distributed representation and finding much more general features and then mix them. And for example, you can have the features vertical, horizontal, rectangle and ellipse. And if you combine and share these features, you can represent your geometric shapes. So think about now what happens if a new shape needs to be represented. So for the localist representation, you need to add a new dimension. And as you can imagine, for natural images, or if you take sensor measurements, every time something changes, you will need to find a new representation, and this can get very, very complex over time. So you need a very complex model to find patterns and structures in your data. In contrast to this, if you use a distributed representation, you can represent the shape with existing dimensions. So here's a summary showing the difference between the localist and the distributed representation. For the localist representation, so one feature describes each thing. This is quite easy to understand, and also it's easy to model, but as soon as the data has a componential structure, it gets very inefficient. Methods like decision tree and k-nearest neighbor use this localist representation. This is also the reason why they are not able to find complex structures and patterns in your data. Methods like deep neural networks are much better in doing this because they work with distributed representations. So the features are shared, and also because they work with distributed representations, they are able to disentangle the underlying factors of variation. So to sum up, representation learning is a core element of deep learning with neural networks. So neural networks is not a classifier, it's not a regression method. The core of neural networks is representation learning, and only the very last part in neural network decides on what you want to do. We will talk about it in more detail in the next lectures. A good representation is always connected to your intended task. That's why neural networks are so powerful, because you tune your data representation at the same time while solving your specific task you want to solve. And it helps to achieve a higher accuracy and interpretable results. And this is related to the disentanglement of the underlying factors of variation. And also representation learning helps to learn with complex data. So it's very hard to deal with complex data in general, but if you change the representation, you might be able to work with these relevant informations in your data, which are necessary to solve the intended task. And so I hope you got more insights in what representation learning is. This is the basis for the next lecture, when we talk about what is a neural network, what is deep learning, and we start with specific models like convolutional neural networks and recurrent neural networks. And thank you very much for your attention, and I hope we will meet in the next lecture. Thank you.